Hello, a very good morning to everyone. Here we are to the final part of the video lessons for chapter 2, where in this part of the videos, we are going to talk about electronic configurations of ion and positions of elements in the periodic tables. Right, so we know that in the previous lesson, we have already learned how to fill in the electronic configurations for the elements in the periodic tables, including the D blocks elements. And we have already learned on how to apply the three rules and principles, which is up-bound, Pauli exclusions, and also Hunt rules. So we are going to continue on with the electronic configurations of ions in here. So how is ion formed? So an ion is formed when an atom or molecule donate receive electrons. Yeah. Okay, so it can be a positive or negative charge. So a positively charged ion is also known as cation, whereas a negative charged ion is also known as the anion. Yeah. So a cation is formed when electrons are donated. Okay, so for example, if you have sodium with the electronic configuration 1s2, 2s2, 2p6, 3s1, so you donated one electron to become Na plus E minus. So now in the Na plus, you donate the electrons from the 3s1, right? So whereas for magnesium, okay, where you have a 1s2, 2s2, 2p6, 3s2, you donated 2 electrons to form Mg2 plus. So an atoms or molecule accept or donate electrons to achieve an octet configuration of 2s2 to ns2 and p6, which is more stable here. So that is why they accept or donate electrons. Conversely, as for negatively charged ion, how is negatively charged ion is formed? Negatively charged ion is formed because electrons are received. So, for example, if you have fluorine 1s2, 2s2, 2p5, you accepted one electron and form 1s2, 2s2, 2p6 to form fluoride ions. All right. So another one is oxygens. So you have 1s2, 2s2, 2p4. You accepted 2 electrons to form oxide ion of 1s2, 2s2, 2p6 in here. Okay, so all of them has form ion in order to achieve the octet configuration. Now let's have a look at more examples here. Right, so in the aluminium, originally you have 1s2, 2s2, 2p6, 3s2, 3p1. Now when you remove electron from here, from what you can see, when you're filling in electron, you're filling according to the Aufbau principles, which is from the lowest energy levels to the highest. And conversely, when you remove electron, you have to remove it from the highest back to the lowest in here. So in this case, you are first going to remove electron from 3p1 and then the 2 electron from 3s2. So that is why in aluminum 3 plus, you have 1s2, 2s2, 2p6 in here. So similarly, so since electronic configuration of the phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So now when you become p3 minus, you accepted 3 electrons in here. That is why at the end of the day, you have 1s2, 2s2, 2p6, 3s2, 3p6 in here. So zip. Okay, then the next one, vanadium. So vanadium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. So when you donated 3 electrons to form V3 plus, so the first 2 electron is removed from the 4s orbital first. Only then you remove the electron from 3d in here. So always remember, after electrons are filled, 4s is slightly higher than 3d. So that is why when it comes to removing electrons, you of course remove from the higher energy level, which is 4s. Only then you remove 3d. So for vanadium 3 plus, you form 3d2 in here. And then another example is N3 minus. Original electronic configuration of nitrogen atom is 1s2, 2s2, 2p3. So when you form 3 minus nitrogen ion, you add 3 more electrons to form 1s2, 2s2, 2p6. As for Fe2 plus, originally Fe has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. So you remove 4s2 in here. two electrons. So that's why you have 1s2, 2s2, 2p6, 3s2, 3p6, 3p6. And then in the gallium originally you have 1s2, 2s2, 2p6, 3s2, 3p6. Okay, you have got 3d10, 4s2, and also 4p1. So if you were to remove 4 electrons in here, because the first is removed from the 4p, second and third is removed from the 4s, and then finally the fourth electron is removed from the 3d in here. So that is why you have gallium 4 plus with 3d lines in here. As for the negative charge ion in south S4 minus, so originally S you have 1s2, 2s2, 2p6, 3s2, 3p4. So when you add 4 electron, so 2 will go to the 3p, it will make it become 3p6, and then you have 2 more, which is really the next energy level, which is 4s. So that is why S4 minus, you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then finally, for the bromide ion, originally you have the valence electron of 4s2, 4p5. So you just add 1 more electron to form 4s2, 4p6. So that is how you write the electronic configurations of the ions. And one more term that before I forgot it, like in this case, you see ions such as aluminium here. Okay, you notice that both aluminium ion and nitride ion has the same number of electrons. So for if you have the same number of electrons in here, we have terms for it. We call them as isoelectronic. Where you have species with the same number of electrons. So that is what isoelectronic from here means. Okay. Okay. And to wrap up our chapter 2, we are also going to look at the classification of the element into SPDF blocks in the periodic tables. So generally in the periodic tables, all elements can be classified according to the blocks where depending on their valence electron, that is where the blocks are situated. Okay, all right. So going vertically, you have what we so call as the period. And going horizontally, you have what we so call as a group here. Okay, so therefore, let's identify one by one. So going down from here to here, okay, all of this is group 1 element. Okay, so you have group 2, okay, you have group 13, okay, you have group 14, okay, you have group 15, right? You have group 16, okay? You have group 17, and finally you have group 18 in here. Okay, so how are these groups being classified? They are classified based on their valence electron. All group 1 elements will have the valence electron of ns1. Okay, they have the valence electron of ns1. For example, lithium 2s1, sodium 3s1, potassium 4s1. And then if you are from group 2, all of them has the valence electron of ns2. Okay, beryllium 2s2, magnesium 3s2, calcium 4s2, and so forth. If you are from group 13, you have the valence electron of ns2 and p1. Okay, for example, boron 2s2, 2p1, aluminium 3s2, 3p1, gallium 4s2, 4p1. Okay, then they are classified as group 13. If you have valence electron of ns2 and p2, okay, so you have the group 14 in here. So for example, carbon 2s2, 2p2, silicon 3s2, 3p2, germanium 4s2, 4p2, and then you have valence electron of ns2 and p3. Okay, So they are on group 15. So nitrogen 2s2 2b3, phosphorus 3s2 3b3, arsenic 4s2 4p3. Okay, and if you have the valence electron of ns2 and p4, okay, you have group 16. Okay, oxygen 2s2 2p4, sulfur 3s2 3p4, selenium 4s2 4p4. Okay, and if you have a valence electron of ns2 and p5, okay, you have a group 17 here, right? So chlorine 2s2 2p5, chlorine 3s2 3p5, bromine 4s2 4p5, and finally you have ns2. This is for helium specifically, and if you have an ns2 and p6, okay, they are all from group 18 in here, okay? So helium 1s2, neon 2s2 2p6, other 3s2 3p6, and krypton 4s2 4p6 in here. So for helium, such configuration is known as a duplet, and when any elements that have the ns2 and p6, we call it as an octet configurations in here. Okay, okay. So other than this now, if you notice carefully, since all of the valence electron in group 1 and group 2 ends up with the valence electron filling as S in here. So that is how they are classified as an S blocks element. And then if you notice carefully, all of these valence electron will end up as a P in here. That is why they are all classified as a P block elements in here. Okay. All right, then we have another block which is made of the valence electron, including the partial filled d orbitals. Okay, so you shall have, for example, 4s2 3d1. Basically, they have the formula of n as 1 or 2, n minus 1 d in here. Okay, okay. So if you have the valence electron ns2 4s2 3d1, you are from group 3, ns2 4s2 3d2, group 4, 4s2 3d3, group 5, 4s1 3d6. This one is anomaly that I talked to you previously, group 6, 4s2 3d5, you have group 7, 4s2 3d6, you have group 8, 4s2 3d7, group 9, 4s2 3d8, group 10, 4s1 3d10, of course, this is also the anomaly, you have group 11, and 4s2 3d10, you have group 12 in here. So basically, the classifications of the elements will depend on their valence electron. So be careful with the terms that we use in here. If let's say we say valence electron, then we will express the valence electron as like n as 2 n p something, right? Depending on what you have inside here. But let's say we take let's say for aluminium instead. Okay, we say that the valence electron of aluminium is 3s2 3p1, right? Okay, 3s2 3p1 in here, right? Okay, so number of valence electron, we say that is 3. Okay, then another term is valence orbitals. The valence orbitals for aluminium is 3s and also 3p. Okay, so these are the terms that is frequently used in Stpm to test the students. So I hope that you'll be careful in this sense in here. Okay, okay. One more thing to worth taking notes in here is if you have number of valence electron 3, not only that you can have possibly 3s2 3p1, but there is also a chances that if you have a number of valence electron is 3, it can refer to the d block elements in here, because scandium also have the number of valence electron as 3 also, titanium is 4, vanadium is 5, chromium is 6, manganese is 7, and so forth in here. So whenever you see number of valence electron is 3, 4, 5, 6, 7, it could represent group 3 or group 13. group 4 or group 14, group 5 or group 15, and so forth. Okay. So look at the description on how they are going to describe the elements, and I'm sure that you have the idea of what are the elements that they are talking about, right? Okay, so finally, we have what we so-call as an F blocks element. Okay, so in the F blocks element, where all the elements are filled with a partial field F in here. So for example, 6s2, 4f1, 3d5d1, so you have 4f1. So that is where it is an F block element. Okay, so 4f3, 4f4. So all of these are showing a partial field F element, orbitals and electrons and f orbitals here. So that makes them an f blocks element, right? Okay, so with that, I think that is all for the final part of the video. I hope that you like it so far, and see you all in the next video. So next video, we are going to move on to chapter 3, all right? Okay, have a good day.